My name is Rohan Aluri, and this is my Physics 2211 Oscillations Lab. Some of the intended goals of this lab were to observe the motion of an object attached and oscillating on a spring, and to use Tracker to create an experimental model for the object's motion, to create an accurate and up-to-date computer model of the object's positional movements by using the physics concepts of Newton's second law and the conservation of energy formula, and to subsequently compare the two models as well as the predicted and observed motion, and explain any similarities and differences that were noticed. These concepts are all important for us to understand the sinusoidal motion of various different objects. Some of the physics concepts that were explored were Newton's second law, the force of the spring and Hooke's law, and the net force formula, which can all be seen in the top left. At the bottom, we are introduced to a new concept known as energy, in which the system can be seen to be the mass, the spring, and the earth. The total energy in this case would equal 0, and therefore mean that no work would occur. This can be seen due to no external forces acting on the system. The values for kinetic energy, the spring energy, and gravitational energy are also displayed as well. Some of the different procedures that were taken in this lab were to initially record a video of an identified object moving in system oscillation on a spring in harmony, to then upload the same video to the Tracker software and gather the experimental data, and then create an experimental model using appropriate conventions for the motion of the object, to then create a computational model for the motion of the object via GlowScript and the provided starter code, and to then discuss and analyze the findings. In this video, you can see the experimental data that occurred via Tracker. I pointed the different center of masses at all the different positions, and you can see the respective X and Y positions at the various different times. In the top right, you see a graph of the X position and time, with also the Y position and time. From this Tracker software, we got some data values which can be seen as the initial position, initial velocity, mass, and the period. The mass and the period are two very important values that we should identify. For the gravitational force, we see that force is equal to mass times gravity, and there are no other forces other than gravity in this situation. So therefore, we do 0.403 times the vector 0, negative 9.8, 0, and get the resultant to be 0, negative 3.940 newtons. We then can also calculate the spring constant and the relaxed length. We found the spring constant using the period formula for a spring and got the spring constant to have a value of 6.87 Newton meters. The relaxed length of the spring was also seen to be by setting the gravitational force equal to the spring constant formula, and then getting the relaxed length of the spring to be 0.127 meters. Following the experimental model, we can see my code and the computational model that was seen via GlowScript. On the left, you can see how I changed and edited the lines such as initial position for the vector and the velocity vector, and to also change the time and add the mass of the ball as well. On the right, you can see how the gravitational force was added as well as my spring constant and the relaxed length of the spring. The next image shows additional code that shows how the time is below the final time that I identified, and how I defined the initial energies by setting them equal to their initials and calculating values such as the gravitational force, spring force, and net force, and by finally at the bottom calculating the total energy change that occurred throughout the lab. As you can see from these images, the top left shows the X position versus time, the top right shows the Y position versus time, and the bottom shows a change in different energies over time. In all graphs, you can see the same oscillatory patterns with this curve, has one leading strand and one lagging strand, to show how the values are similar, but they can have discrepancy due to factors such as air resistance or drag. Upon reviewing and further analyzing my model, it could be seen that the energy principle is in fact satisfied for the model system. This is due to the overall change in energy being able to sum out to be 0, as seen by the different color oscillatory patterns for the signed energies. This theorem aligns with the energy principle as the change in overall energy remains zero because there are no external forces and the entire system is only in consideration. Additionally, I calculated the period from the y data and the period from the x data as well. The difference in these periods may be due to friction forces such as drag or air resistance, which in turn affects the calculation for the spring constant, also known as K, as it is calculated using the x and y period data above.